Hmm. So welcome everyone. So today I'm going to discuss missions from 2008 to 2023. Maybe I'm not covered all these years today itself, but I'm going to cover all these years from the upcoming sessions also. So before going into the session, so let me introduce myself. Okay. So I have done my MTech in IIT. So my good gate rank is 780. So currently I was working in JE in MES department, that is military engineering services. Okay. So recharging, which of the following DC generators is used? If you see for the battery charging, we need constant output voltage. Okay. So for the constant output voltage, we usually use shunt generator. Okay. Shunt generator. So from the exam point of view, there are some questions they will ask like applications of shunt generator. Okay. Generally, shunt generator we use for general lighting purpose because it will give constant output voltage so that even there is load variation, output will be maintained constant and there is no blinks. Okay. And the second purpose is it is used in small lathe machines. Okay. Small lathe machines and it is used as portable generator. Portable generator. Okay, these type of applications they will ask in the exam point of view. Okay, so coming to this question, the answer will be the DC shunt generator. Okay, and coming to second question, the no load speed of DC series motor. Okay, so coming to DC series motor, in DC series motor, the field winding is in series with the armature. So in case of no load, the armature current will be zero, right? So we know that E equal to Ka phi into omega. So field is in series with the armature current. So field flux is also proportional to armature current. So E is proportional to armature current into omega. So armature current is inversely proportional to 1 by omega, right? So if it is zero, so this will be infinite, right? So usually you usually listen a word, like you usually listen a statement in your beat. Never start DC series motor at no load, at no load. Because the speed will be infinite. In throttle, the speed will be very high. So the mission may damage. Okay. So for this, the answer is very high. Okay. Coming to the third question. So this is also a good question. The purpose of the conservator in a transformer. Okay. So let me explain you the basic uh, outline of the transformer. So this is the transformer tank. Okay. So in this, the oil will be filled and the winding will be also placed. So from this tank, there is a relay, Buckos relay, and on the top of it, there is a conservator tank. There is a conservator tank will be there. It is of cylindrical shape. Okay. From this, from this, a breather is connected. Like this is the conservator tank, and this is the breather, and this rectangle is silica gel. Okay. This rectangle shape is silica gel. Now the purpose. Suppose if the load is more, then the current will be more, the heat developed will be more, right? So the eye will get expanded. The eye will get expanded. So this oil, so this oil will travels to the conservative tank because the oil needs some space to be in that arrangement. So the oil will go to the conservative tank and will store here. So the air, the air here in the conservative tank will be breathed out through this breather. So the air will be breathed out. Breathe out means it will go out through the breather. So during overload condition, the conservator will take the oil into the conservator tank. Suppose if the load will be less, so oil get contracted, right? So oil get contracted. So the oil in the conservator tank will again come to the transformer tank. So this what the breather will do from the atmosphere. Okay, from the atmosphere, air will be taken into the conservator tank. Taken into conservator tank. This is called breathe in, right? So the name itself suggests that breathe in and breathe out. So the air will be taken into the conservator tank. Now the problem is with the atmosphere air, moisture is also there, right? If the moisture will also come into contact with oil, then dielectric strength will reduce. Okay, so in order to prevent this condition, what we will do is we will use silica gel. Okay, we use silica gel. So silica gel, by using silica gel, the moisture content will not come inside the conservative tank. So coming to this question, the purpose of the conservator. So conservator, what is doing? While overloading, the oil is taken into that. While underloading, the oil is coming out of the conservative tank. So we can see take up contraction and expansion of the oil. So this moisture is, I already said, silica gel, and cooling is by oil. So generally here oil is used for two purposes. One is for insulation and other is for cooling. Okay. So in general, for high rating transformers, oil cooling is used, oil cooling only used, but generally for low rating, air cooling also used. Okay, air cooling also used. So for this particular answer, the purpose of conservator is to take up contraction and expansion of the oil. So this is the static question, like this is direct we can attempt. So in case of power transformer, the no load current in terms of the rated current. Okay. So coming to the transformer, it is 2 to 6% of the full load current. Okay. This is in case of transformer. But in case of induction motor, if they ask the no load current, then that will be 30 to 40% or 30 to 50% of the full load current. Okay, that is in case of induction motor. Coming to transformer, it is 2 to 6%. So answer will be B. Okay. Now coming to fifth question. So the copper loss at the 7 by 8th load, 8th of the full load is 4900. What is the full load copper loss? Okay. Generally, copper loss at any load, okay, copper loss at any load is equal to x square of copper loss at full load. So x is the fraction of the load. So here they are given at the 7 by 8th load, that equal to 7 by 8 square into copper loss of full load. So this is given as 4900. So 49 by 64 into copper loss at full load. So 49 hundredths. So copper loss at full load equal to 6400 watt. So this is answer B. Okay. Now coming to sixth question. So sixth question. Okay. So 500 kVA 200 H transformer is operated at 50 H. So the frequency rating is changed now. So will the kVA rating is changed or not? Let's see. Usually the transformer kVA is directly proportional to the E. So E equal to E equal to 4.445 Fn. So E is proportional to F. So S is proportional to F, right? So given S1 by S2 equal to F1 by F2. So at 500 kVA, the frequency is 200 Hz. Now at 50 Hz, what is the kVA rating? Okay, so 54 is a and ST equal to 4 125. So 125 kVA. Okay, now let's go to seventh. So the power factor at which transformer operates. So this generally the transformer is connected to a load, right? So based on the load power factor, like if we connect resistive load, it will operate at unity power factor. If we connect RL load, it will operate at lagging power factor. If you connect RC load, it is operated at leading power factor. So based on the type of the load, so the power factor of the transformer will operate. So answer will be the D. Okay. So coming to eighth question. Okay. So eighth question. See. So the efficiency of 100 kVA transformer is 0.98 at full load as well as off load. So if you write efficiency equal to X into kVA rating at full load by X into kVA rating plus X square into copper loss at full load plus iron loss. Okay. General efficiency. So here they given that at full load and off load, the efficiency will be 0.98. So 0.98 equal to S at full load by S full load plus copper loss at full load plus P iron. This is equation 1. And similarly at off load means X equal to 0.5, 0.5 SFL by 0.5 SFL plus here X square. So X square means 0.5 square, that equal to 0.25, right? 0.25 copper plus iron loss will be constant loss. Okay. So now what I will do is, if you observe 1 and 2, both are equal because LHS part is 0.98 at both sides. So what I will do is, I will equate 1 equal to 2. Okay. So SFL by SFL plus P copper plus P iron equal to 0.5. So what I will do, I will multiply with 2 on numerator and denominator. So the numerator will become SFL, the denominator become SFL plus 0.5 copper plus 2 into P iron, right? So now these two will be cancelled and let make it 0 SFL plus 0.5 P copper plus 2 P iron equal to SFL plus P copper plus P iron, right? So this 2 will cancel. So you will get 0.5 P copper equal to P iron. That implies P copper equal to 2 times of P iron. So copper loss will be greater than iron loss. So the answer will be the copper loss is more than the core loss, option C. Okay. So no need to solve, no, no need to use this 100 kVA. Okay. And this 0.8, even if they haven't given this data, you can conclude which is more and which is less. Okay. So coming to ninth question. Okay. Coming to ninth question. Which of the following will improve the mutual coupling between primary and secondary circuit? Okay. Let me tell you some basic things. Suppose there is a core and there is a winding. Okay. So if you supply this winding by voltage V, there will be current will flow and the flux will develop, right? The flux will develop. So if I place a iron core, this is core 1 and let it be core 2, iron core near to the core 1. So the flux, so there will be flux, some part of the flux will be linked with core 2, right? So like let the core 1 develops flux phi 1. Okay. the flux linked with the core 2, that will be phi 2, that will be some k into phi 1, because suppose there are 100 lines of flux is coming from the, okay, there is 100 lines of flux coming from the core 1, then there is a chance that 90 lines of the flux will linked with core 2 and 10 lines will not be linked with core 2, right? So I expressed that in terms of phi 2 equal to k into phi 1, okay, like phi 2 equal to 0.951 coming to in this case, okay. So this k represents coefficient of coupling, okay, coefficient of coupling. So if this k will be more, then more flux will be linked with core 2. So there will be a mutual coupling between, there will be good mutual coupling, okay, there will be good mutual coupling between the core 1 and core 2. So I hope you understand what is mutual coupling. Now coming to the transformer case, this is first winding, this is, I mean, this is primary winding and this is secondary winding, okay. Now the flux will go through this path, right, right. So the flux has a path of the core, right. If the core having low reluctance, okay, if the core is having low reluctance, let it be, you know, phi equal to mmf by reluctance, right. So if the core is has less reluctance, then flux will be more. I mean, so if the core is of low reluctance, then the more flux will be linked with phi 2. If more flux is linked means there will be good mutual coupling, right? There will be good mutual coupling. So if the reluctance of the core is high, then the I mean, if the reluctance of the core is high, then very less, or you can say less flux will be linked with the secondary. Okay. So here they asked that improve the mutual coupling. Improve the mutual coupling. So we need more amount of flux to be linked with secondary winding. So we need low reluctance magnetic core. Okay. So this is the answer for the question number 9. Now question number 10. Okay, question number 10. So high leakage transformers are of which rating? Okay. So this is also based on that mutual coupling concept only. Now, if the mutual coupling, okay, if the mutual coupling is not good, then there will be leakage, we can say. Because of the leakage flux, then we can say there is less mutual coupling. So due to this, there will be the leakage inductance, right? Inductance. Okay. So if this leakage inductance is high, okay, if this leakage inductance is high, there will be high energy loss, and we can say suppose this is leakage inductance, this is E1 and this is the V1. Okay. So if this is of high leakage inductance, there will be voltage drop will be more, and we will get V1 is less. Suppose it is 230 volt and the drop is of 100 volts, we only get 130 volts, right? So due to the high leakage inductance or high leakage of flux, I mean high leakages, the voltage we will get will be less. Okay. So what we will do is we usually generally use small voltage and small current rating transformers, because small current ratings, okay, because even for this purpose if you use, so the voltage will not be more than the rating, so it will be efficiently used, right, it will be efficiently used. So the answer for this question is small voltage and ampere rating. Okay. So coming to 11th question. So here it is mentioned that a transformer is working at full load and its efficiency also maximum at that full load. Okay. So the iron loss is given 1000 hours. So iron loss equal to copper loss at maximum efficiency, that is 1000 watts. and it is said that it is at full load. So copper loss full load equal to 1000 watts. Okay. So they asked that copper loss at off load. So copper loss off load is 1 by 2 square into copper loss at full load. That is 1000. So it is 250 watt. So answer is 250 watt. Now coming to 12th question. So distribution transformers to have maximum efficiency nearly at. So if you see distribution transformers, they are usually near to location of the consumers, right? Consumer and distribution transformers will be there. So there is a load fluctuations at the consumer's end. So that's the reason distribution transformers are never designed to operate at full load. Okay, never designed to operate at full load. So distribution transformers is designed at 50 to 70% of the full load. Okay, so power transformers are usually designed near to full load. Okay, okay. So the answer for this is 50% of the full load. Actually 50 to 70%, but we will go with the options. Okay. Next question number 13. Okay. So burden. Generally this is definition type. Generally burden is the how much load on the secondary winding of the transformer. So usually in transformer it is expressed in terms of VA. Okay, means volt ampere rating. So volt ampere rating. So this is generally basic definition type one. So the answer will be B. Okay. Now, hmm. So coming to 14th question, this is Winburn test, right? So generally, Winburn test is applied on the motors. Okay. So out of the given options, only option A and option D is are of motors. So option B and option C can be eliminated. So generally, Winburn test is a no load test. Okay. So Winburn test cannot be applied on the series motor because series motors never run on load, right? Second, Swinburne test is also called as indirect loading test. Indirect loading test. Let me tell you why it is called indirect loading test. First, usually it is called no load test, right? So from no load test we can get iron loss, right? Now, now, so from no load test we got iron loss. Suppose mathematically I assume that my current is at full load, or that is 100 amp. So mathematically I can calculate copper loss by I square or formula like 100 square into the winding resistance. So mathematically, I can calculate the copper loss at any particular load. So by means of that efficiency, I can calculate because I know the losses. As I know the losses, I can calculate efficiency without loading the test. So without loading the test, I am doing this efficiency calculation. But this is not accurate efficiency, but still I am doing efficiency calculation without loading the test. So this is called indirect loading test. Given two winding transformers of 2000 volt and 200 volt. So now it is used as an auto transformer. Like let me draw that. So they mentioned that it is 2000 volt. So if I take additive polarity, so then this is 2000 volt. I mean, sorry, this is not additive polarity. This is it up. Okay, let me take this here 200 volt. So the total voltage across it is 2200 volt. Okay, 2200 volt, right? So given rating is 20 kVA, right? So rating of the auto transformer equal to rating of the two winding transformer divided by 1 minus K, where K is LV by HV, low voltage by high voltage of the auto transformer. So K is low voltage is what 2000, by high voltage 2200. If both will be cancelled, 10 by 11. So rating of the auto transformer will be 2 winding transformer rating is 20 kVA, which is given by 1 minus 10 by 11, which is equal to 220 kVA. So this is the answer. So option B. Okay, coming to 16th question. So 16th question, power transformers are designed maximum efficiency at. So it is already discussed. Distribution transformers are generally designed at 50 to 70%. Power transform is nearly at full load. So option will be B. Okay, coming to 17th question. In a single phase transformers, the copper loss at full load. So copper loss at full load is given as 600 watt. At half of the full load, the copper loss. This is also easy. Half load, they ask copper loss at half load, which is equal to 1 by 2 square into copper loss at full load. So 600 by 4, that equal to 150 watt. This is repetitive bit. Okay. Now coming to 18th question. So an auto transformers used with sodium vapor lamp should have high. Now if you see this, suppose this is the lamp. Okay. This is the sodium vapor lamp. Usually we use the ballast. So and then it is supply. So generally if you take this is 230 watt and this is ballast. Okay. So it is like an inductor only. Okay. It is like an inductor only. Now generally there is a gas present here. Okay. So we need to ionize that gas. We need to ionize this gas, so that the light will mechanism will start. Okay. So if we need to ionize that gas, the voltage required is greater than the supply voltage. Usually it is of high magnitude of voltage we need. So what we will do, we need to produce the voltage across inductor will be high. The voltage across inductor, or to get voltage across inductor, okay, will be more. Suppose this is an inductance. Okay. So we need more voltage, means we need more drop, right? So if leakage inductance will be high, okay, so that means the voltage drop will be more. So this uh, drop will be used to ionize that gas. So the answer will be leakage reactance of the winding should be high. Okay. Uh, Coming to 19th question. Okay. So 19th question. So here they are given number of turns of the frame. Okay, let me draw the auto transformer. Okay. So the primary turns is 210 and secondary turns is 40, 140 or 140, and the input current is 60 amperes. So this is V2 and this is V1. Okay. So we know that V1 by V2 equal to N1 by N2, right? So that implies, so and we also know that V1 I1 equal to V2 I2. So I1 by I2 equal to N2 by N1, which is equal to N2 is 140 by 210. So I2 equal to I1 into 210 by 140. So I1 is 60 into 210 by 140. So 2 is a 3 is a 230. So I2 equal to 90 amperes. So this is 90 amperes. If you see this diagram, the current is entering here with the first dot. They should be leave the dot at the second terminal. So by nodal analysis, 60 is coming and this is I, and 90 is going towards this. So 60 plus I equal to 90. So I equal to 30 amperes. Okay. This is the common current. I equal to 30 here. This is the common current and this is the secondary current. Okay. I asked output current. Output current is 90. and common winding current is 30. So option C is the answer.